Hi. Um, so, hold on one sec. So let me say a few things before we get started on today's sort of math lecture. Let me say a few things about tomorrow. So tomorrow is an important day for this class because it's going to be the day of our midterm. Now I've sent out a few times now a document outlining the procedures for this second midterm. So if you look at that document, everything that I'm about to say is presumably written there. So please take a look at it and make sure that you fully understand it. It's very, very important that you understand how this whole thing is going to work. It's going to be a group midterm. And so what that means is, this is what it means for you. Tomorrow morning, you're going to join a Zoom meeting, okay? And I will give you a URL for a Zoom meeting. You'll join it, I will join it, and then what I'm going to do is break you up into groups of about 3 people, okay? You will then, the way that those groups work is Zoom has a feature called Breakout Rooms. You'll go into these breakout rooms and you will be able to talk amongst yourselves about the problems on the midterm. Okay, and you can say whatever you want. I'm not interested or in regulating what you can say or anything like that. But that is and then you'll do your problems. Each of you will submit your own copy, your own written out copy of the midterm to me via email. How will you do that? You will do that in the same way that you've been doing your post-lecture slips and that you've been doing your homework. You will take pictures of them with your phone, attach those images in order, please, to an email that I sent to you in the morning. And that's how you'll submit your midterm. Now, in terms of timing, you need to show up to the Zoom office hour, the Zoom meeting for the midterm. You need to show up for that on the hour. So if you are enrolled in the 8 a.m. section, you show up at 8 a.m. to the Zoom meeting. If you're enrolled in the 9 a.m. section, you show up at 9 a.m. If you're enrolled in the 10 a.m., etc., you show up at 10 a.m. I stick you into these Zoom breakout rooms. That should take about, at most, 5 minutes, I'm really hoping. It's not a big snafu, but I'm going to put you in these Zoom breakout rooms. Included with the email will be the problems. So I'm going to be sending out, actually, from my end, I'm going to be sending out 3 emails, okay? And these emails will arrive to you 5 minutes before. This is going to be a juggling act. 5 minutes before the midterm is to begin. So you'll have a copy of the problems in your hot little hands 5 minutes before the midterm begins. Then the midterm will start 5 minutes later. I'll break you into groups 5 minutes later. You'll have 50 minutes to work on the problems together. And then after, like for example, if you're enrolled in the 8 a.m. section, at 8:55 a.m., the time will be done, and then you'll be given 10 minutes to submit your midterm. And again, that's as simple as taking a picture of each of the pages of the midterm, making sure that your pictures are not blurry so that I can read them, and then submitting the midterm via email, sending an email to me by responding to an email that I will send you in the morning. Rules and stuff like that. So you're obviously allowed to talk to your group members as much as you like. You are also allowed to use whatever notes or homework or whatever resources that you have available to you. You are allowed to use those. But what I ask that you not use is 2 things. The internet, I ask that you not use the internet. And I also ask that you not use other people. So sure, if you're very slick, you could presumably hand off your midterm to some other person, like some calculus 2 ace or whatever, and try to get them to solve the problems for you. Sure. But I ask that you not try to do that. Now, you should know that, you should know one thing, or a couple things, I guess. First, I'm the chair of the Academic Integrity Committee on our campus. And so I've seen a lot of stuff happen. And I know that there is a perception among some students that they can get away with some really dastardly cheating scams or whatever. All I can say is that, one, I'm really not as stupid as you might think I am, okay? I'm not naive, and I don't turn a blind eye. So if I see you doing something, if I see you cheating or something like that, I'm going to take both you and me into the depths of hell. I'm going to spend a lot of time writing letters, setting up meetings, and arguing, because I despise cheating. Okay, I absolutely hate it, and I won't tolerate it. Okay, so like I said at the beginning of the semester, think of this as being sort of a pre-commitment. Okay, a pre-commitment right now to not to having a zero tolerance policy on this cheating thing. Okay. In particular, one of the things that I presume could happen is that you could send your work to another student by like taking a picture of it, sending that picture off to some other student or something like that, because they ask you to, or even because they paid you to. And as the chair of the AIC, I've seen cases in which one student has offered a bribe to another student, and that just sort of going completely awry. Please be aware that if you give up your information, the information on your exam, to other students can use that in whatever way they wish. So you might say to them, because you think that you're being kind to your fellow student, you might say to them something like, okay, I'll give you my answers, but don't just straight copy them. Do something to make them look different or whatever. And you know what? Sometimes students do that and still get caught. And sometimes students just straight up copy exactly the thing that you wrote down, which makes it super easy for us, as far as our job is concerned, to identify such students and identify the person that they copied from. And then both of you find yourself in hot water. Okay? So please, I'm not stupid. I'm observant. I can look at your work and I know I have a sense of whether or not it is yours or not, because I've come to know you over these few months. Please do not try to cheat, okay? Just think of it, please don't try to cheat, okay? This is not a high stakes enough thing to make it worth the ethical disaster that you would be bringing upon yourself, okay? Let's try to do well, okay? Good. So let's see, what topics are fair game for the midterm? Well, I think that there's 5 topics that we haven't been since the last midterm. 5 big topics. The first one is partial fraction decomposition. The second is center of mass. The third is improper integrals. The fourth is sequences and issues related around that. And the fifth is series. Now, series is a big topic. We're going to be talking about series for the rest of the semester. So I'm only talking about the content that's on worksheets 22 and 23 as far as series are concerned. That's the material which is fair game for the exam tomorrow. And I put out a practice midterm yesterday. You might want to take a look at that and try to write through that today. I'm going to release solutions to that practice midterm tonight. Okay? But if there are any questions as to what's fair game and what's not, you can ask during office hours or whatever. I'm sorry, I don't think I have... Oh yeah, I do have Twitch chat open. Okay. Let's see, is there anything else I want to say? If anybody has any questions about the midterm, now is a good time to ask in the Twitch chat. Yeah, if you have some problem with this, if you have some issue with this, okay, because I know some people have limited internet access. I know some people just have life circumstances which are making this extremely difficult. I'm not interested in putting you out. Aaron asks, is there a specific way I am breaking up the groups? I'm keeping that a secret. Okay, I will break up groups. I do have a method inside my head. It's not going to be random, but I'm leaving that up to me. I'm leaving it to my discretion. Okay. The important thing though is that you show up, and that would it be okay to communicate with our group via text, or would I not recommend this? I would recommend that you just do it via Zoom. Claudio, I know in particular you've got a good Zoom setup, so I don't see any reason why you wouldn't just use that. But I guess I just don't see any advantage or reason to do it. But I don't like. Oh, that's not you. How's the okay? There's not two Claudios in our class. Whatever. What? I'm so confused. What? What am I talking about? Oh, text. I hate to give rules because I don't like rules if I don't have to give them, but sure, I guess. But with the proviso that, you not provide full solutions, like via an image or something like that. That's all I have to say, I think, about the midterm. Make sure that you show up, okay? I know that I reduced the percentage that this of your final grade that this midterm is worth because of this whole coronavirus disaster. But it is extremely important still, right? It's the difference between, for many of you, it's going to be the difference between a C or a D, which means that either you get out of Calc 2 or not, or even a D or an F, which might mean that you have to take the class over again. So please take it seriously and show up. Okay, if you can't show up, you need to make arrangements with me today. All right, it's extremely important. All right. So I want to talk about math now. I think. Gosh, I hope I'm not forgetting anything. Yeah, if you have any questions, please share. And oh, right, I do want to say that today I'm going to be having office hours in a Zoom meeting. From 9 to 11 a.m. as that's the usual thing that I've been doing. The URL for that Zoom meeting is in your email, so check that. And then I'm also going to have an additional office hours set today at 8 p.m. Okay, for those of you that are night owls. So please come on out and we can talk. All right, I need a blank sheet of paper. Oh, and I should switch the scene into OBS. All right, so today I want to talk about the last bit of new information. No, not that one. The last bit of new information that you will be required to know for the midterm, which is what? What is it? It's sorry, let me just fix the chat window real quick. Twitch chat. Okay, there we go. Hey, I'm getting good at this. All right. So the last bit of new information that I would like you to know about, which is the integral test. So this will link. This is not going to be anything new, too new or too heavy. It will very much link back to the stuff that we talked about when we were talking about improper integrals, okay, as you will see. And what the integral test is, I can't tell, if I speak English, what the integral test is a convergence test. Sorry, I have issues, okay. The integral test is a convergence test. So if you're given, so remember what the central question about series is. If you're given a series, the central question is whether or not that series converges or diverges. The integral so we've already learned a couple things. We've learned about geometric series, and we learned that in that situation, for that family of examples, we can fully 100% answer the question as to whether or not that geometric series converges or diverges based upon the value of that parameter r. Remember that parameter r, which represents the multiplying factor that you get, that you multiply the previous term by to get the next term in the geometric series. And depending on whether the absolute value of r is less than or greater than or equal to 1, you can determine whether or not a geometric series converges or diverges. So in some sense, that's a convergence test, because it is informing you. It's a general result which informs you about the convergence or divergence of series. Now, it's a very particular family of series, but it, whatever. It's a statement which is useful, extremely useful. We also learned about the divergence test yesterday. The divergence test says that if an arbitrary series has the property that the limit of the sequence of terms of that series is anything other than 0, then that necessarily implies that the series diverges. See, if the limit as n approaches infinity of a sub n is not 0, then it must necessarily be the case that the sum of the infinite series here diverges. Okay? And we saw some examples of that in action here. All right? That's also a convergence test. That's maybe our second, or if you want to think of it, maybe it was our first real general convergence test. This will be our next convergence test that we learn about, the integral test. The integral test relates the convergence and divergence of series with the convergence or divergence of improper integrals, right? That's the thing I wanted to say. So let's think for a second. So let's think about this this series here. This series is famous, and you know it as the harmonic series. This is the harmonic series that we studied yesterday, and we learned yesterday that this is famously a divergent series. Now, one way that we could, so what is this? This is 1 plus 1/2 plus 1/3, etc. So one way that we could think about this infinite sum of terms here is, well, we could draw a picture, or try to draw a picture of what's happening here. So here's what I want to do. Here's a standard xy plane, and here are some points along here, 1, 2, 3, 4, etc. Now, what I can do is, let's say that what I'm going to do is think about the rectangle which lies above 1 and 2, and what I'm going to do is I'm going to make a rectangle above, sorry, can't talk. We're going to make a rectangle which has as its base this interval from 1 to 2, and we're going to make it have height 1. So I'm going to imagine, I guess this should be a perfect square, that this rectangle here has height 1, and I guess it has width 1, right? So what's the area of that rectangle? Well, of course, the area is 1. Then what I'm going to do is, over the interval from 2 to 3, I'm going to make a rectangle whose area is 1/2. How can I do that? I can do that by drawing a rectangle here whose height is now 1/2, and whose area length here is 1. Similarly, from 3 to 4, I can draw a rectangle, and this height here will be 1/3, and the area of this rectangle will be 1/3. Is it clear what I'm doing, right? And we imagine doing this process more and more and more. Now, where in this picture, I mean, we can see in several places the values of this harmonic series popping up. But one place in particular that I would like you to notice that we can see these values popping up are at the upper left-hand corners of these rectangles, right? The next one would be like here at 1/4, right? And what we could do is connect the dots on those corners there. And I'm going to do that in the following way that's supposed to be evocative. I can connect the dots like this. And I hope that we can all agree, that this blue curve here looks a hell of a lot like the graph of the function 1 over x. Doesn't this make sense, right? Because if we take positive integer values for x and we plug them into 1 over x, you can see that we get precisely points which live on this curve. Sorry, I just realized how not close this camera is to the paper. So does that help? It certainly does. I'm not sure why I'm asking. There we go. That's better, huh? That's better. So we can see that this blue curve here, all right, what this 1 over x is in terms of the vernacular that we established a while back, this is what we call an interpolating function. For what? For the sequence of terms of this infinite series. I'm going to say that 2 more times, so open up your ears, okay? This 1 over x is an interpolating function for the sequence of terms of this infinite series. So the sequence of terms is not the series. The sequence of terms is 1, 1 half, 1 third, 1 fourth. That's what the sequence of terms is. An interpolating function is a real valued function with of a single real variable, which when you shove in one of the positive integer values, which arise as the index for this sequence of terms, you get precisely the value of the sequence. You see what I'm saying? Right? So if you shove 1 into 1 over x, you get 1. If you shove 2 into there, you get 1 half. If you shove 3 into there, you get 1 third, etc. Okay? So that's what we mean by an interpolating function. Again, I'm going to say it one more time. 1 over x is an interpolating function for 1 over n. And what we understand is that, okay, so the value of this harmonic series is, of course, the sum of the areas of these rectangles here, right? Now, it is true that there is a difference between so if we want to relate this series to an improper integral, it is true that there is some error between the sum of the areas of these rectangles and the sum of the areas of these rectangles and the area between the interval from 1 to infinity below and below the graph of 1 over x. It is true that there is some error there, and you can see the pieces of error right there that are sort of not accounted for, or maybe over accounted for by this sum, right? Sure. However, it turns out that that error is not important when it comes to issues of convergence or divergence. It is important when it comes to the issues of what the value of a certain infinite series might be, particularly if it's convergent, but it is not important when it comes to issues of convergence or divergence. And I guess that I just would like you to either take my word for it or to imagine what this same picture kind of looks like when n starts becoming extremely large. When n is very, very large, what tends to happen is this curve here, what it does is it flattens out. It necessarily must, because it's getting closer and closer to the x-axis. And as it flattens out, the amount of sort of overshoot that we have in these rectangles relative to the area under the curve decreases, gets smaller and smaller and smaller. I hope that's clear. It's not so important. All of this is going to get formalized. All of these ideas are going to get formalized in this result, which we're going to call the integral test. So I'm going to write it down now. So what is the statement of the integral test? So suppose we have a sequence. Suppose, let me say it like this. F of x is an interpolating function for the sequence a sub n, which is, so this is now some adjectives that we use to describe f, which is continuous, so that's a mild restriction. Decreasing, this is a little bit more heavy, a little heavier, and positive. So we talked about interpolating functions before. We talked about the way, so I want to sort of say some words about why we need all of these adjectives, continuous, decreasing, and positive. So we talked about interpolating functions for sequences before. We talked about how if you sort of plot out the values of a sequence, there are infinitely many interpolating functions for that sequence, right? All you need to do is just draw any curve which satisfies the vertical line test, which also passes through all of these points. Okay, so, you know, you could have, oh, I'm not passing through the points, but whatever. Okay, so you could imagine that this is a single line and that I'm not, I don't have a broken bone in my elbow. You could imagine that there is an interpolating function, okay? And there are gobs and gobs of interpolating functions. This is not the only one. You could also have one that looks like this. Well, that's supposed to pass the vertical line test. I don't know if it does, but whatever. There are infinitely many. And so in particular, you can have extremely wild phenomenon happening like this, where you have huge dips. I cannot do that very good. But you can imagine that's also an interpolating function, and that you could make this dip go as far down into hell as you want. Okay? So that you have very little control over the value of the improper integral, right? Just if all you were to say that f of x is an interpolating function in this statement, you would have very little control over the area between the graph of the function and the x-axis, and so you would have, you know, the possibilities for the convergence or divergence of the integral would be wild. So we want to control. We want some control over the behavior of the function, of the interpolating function. So we apply these adjectives which give us that control. And it gives us so much control that we can make the following very strong statement. So suppose that we have this, blah, blah, blah. Then, this series, sum from n equals, let's say, 1 to infinity of a sub n, and the integral from 1 to infinity of f of x dx. So this is an improper integral of the type that we learned about a month ago. This is an infinite series, the object that we care about now. And what we can say is that these converge or diverge together. And this is the integral test, and it's important. Alrighty? So, example. I can give you another proof now that the harmonic series diverges, that this series here is divergent. We established it yesterday using a clever grouping argument that I really think is super cool. But we can also establish it using the integral test. So let's just see how that works. So the harmonic series, we have the sum from n equals 1 to infinity of 1 over n. So an interpolating function, it's usually very easy to write down an interpolating function. I had a lot of questions about interpolating functions. One very sort of tried and true method is to just replace the n by an x. This doesn't always work. It doesn't always work because sometimes when you replace n by x, you get something which is nonsense. So for example, if you have something in your, like if you had a sequence of the form 1 over n, negative 1 to the n over n, it wouldn't really make sense to put x there because like what is negative 1 to the 1/2 power, for example, right? that's the square root of -1, which doesn't exist for you, although it does exist for me. Okay, so it doesn't always work, but in many situations, just replacing, just substituting typographically n by x will work out. So that's what we're going to do here. The integral test says that this series, and I'm going to write in shorthand the series like this, and the integral from 1 to infinity of 1 over x dx converge or diverge together. Right? But what do I know? Well, gosh, can I find the sheet, the sheet from the lecture way back when we were talking about something? Remember what this type of improper integral is called? It's what we call a p integral. So let me see, maybe I think I have it right here. God damn, my elbow hurts, guys. It's around here somewhere, I swear to God. Is it back here? Oh, yes. Remember p integrals? This is from way back, okay? P integrals. P integrals are integrals of this form, and what we establish is that they're convergent if p is greater than 1, and it's divergent if p is less than or equal to 1. Okay, we talked about this on March 18th. Okay, so look at that integral right there. Is that not a p integral? Of course it is a p integral. And what's the value of p? P is 1. So you know what we can say? That diverges. So this is a p integral with p equal to 1. This implies divergent. Okay, and so therefore the harmonic series diverges. So this is just another argument for a fact that we already knew. All right, so don't sweat it if you think this is dumb. We already knew this fact. But of course, the argument that we supplied here would be just as true if we put a p here. Right? Now, I guess, oh shoot, maybe I shouldn't have done that. Okay, just pretend I didn't do what I just did. Let's talk about it anew. I don't, fuck me. Okay, there we go. Just pretend I didn't do that. My point is we could apply this same skeletal type of argument not to the harmonic series, but to a series slightly more general of the form sum from n equals 1 to infinity of 1 over n to the pth power. Right? So here's, I'll just make a comment. We can apply this same sort of argument to the sum of 1 over n to the pth power. And what we learn is something called the p-series test. And this is something that's very important and you should know, so I'm going to give it a special box with decorations like this. Okay? The sum from n equals 1 to infinity of 1 over n to the pth power, where p is an arbitrary number. This thing is convergent if p is greater than 1. And it is divergent if p is less than or equal to 1. And I want you to see, so the argument behind this p-series test here, the argument there is the integral test. The integral test is how you justify it. What you do is you you use this statement of the integral test to say that this series here converges or diverges along with, or at the exact same time as when the associated improper integral converges or diverges. But you know that if you write down an interpolating function, that's what you obtain is a p integral. And you know that the p integral is convergent if p is greater than 1, and it's divergent if p is less than or equal to 1, which is this statement. These statements are the same. Okay, they're really reflections of the same sort of phenomenon. You see the parallels, right? All right. If there's any questions, don't hesitate to ask. But that's the p-series, okay? Now, of course, and this is extremely important, we're going to be using this all the time. One thing that I do want to say about this. So what that implies in particular is that if we look at something like the sum from n equals 1 to infinity of 1 over n squared, this is very famous. This is it was I think known for a long time that this was a convergent series, and what we just proved using the p-series stuff and the integral test demonstrates that this is a convergent series. This is convergent because it's a p-series with p equal to 2, and the point is that that's greater than 1, right? So we have that there. Oh, right. So a very big problem in antiquity, not in antiquity, but like 300-400 years ago, was to figure out, well, this converges, but what does it converge to? And I can't resist sharing with you the answer, because the answer is so weird. It turns out that this thing here, and I mean, you can verify this using Python, or I'm super tempted to write a script for you to show you this, that this is true. But it turns out that you can prove that this series here, it's convergent, and it converges to this crazy value. Can you see it? No, you can't. Pi squared over 6. What the fuck? What the fuck is pi doing in... What is pi? Pi, the ratio of the circumference of a circle to... Sorry, the ratio of the circumference of the circle to its diameter. What does pi, why does pi arise in this as the value of the sum of the reciprocals of the squares? So 1 plus 1/4 plus 1/9 plus 1/16. Somehow pi has decided to show up in this calculation. I mean, that's truly bizarre, okay? It is kind of like amazing. It's kind of amazing, and it shows you that there is some really grand unity that exists in mathematics that links all of these things together. I don't know. I think this is absolutely astounding. Just why is pi, this thing that has to do with circles, arising in this? So Aaron asks, on a test, if I was to give you a series like that and ask to prove it's convergent or divergent, simply say the p-series? Yes, I would like that. Would simply saying that by the p-series test, this thing converges with p greater than 1 implies convergence? Yes, that is a beautiful argument. That's an argument which works for me. Yes, this is now a part of your repertoire. You can use this as much as you like, as freely as you like, and I will never question it because I love it so much. Okay. Okay. Well, anyway, that was sort of me, just sort of It's not so important for your life, I guess, or that for your for this course that it's pi squared over 6. I just think that's amazing, and I can't resist sharing that with you. Let's see a problem in which we can use the integral test, okay, to kill a problem. Let's take a look at, for example, this series. So the sum from n equals, let's start n equal to 2 to infinity of 1 over n times the natural log of n. Now it's a little bit confusing looking because we have 3 n's here, but only 2 of them are n's. This one is not an n. That is not an n. That is part of the natural log function, okay? This and that are n, okay? But so don't be confused about that. This is the natural log. So test for convergence. This is what I want to do here. So when I write this test for convergence, what I mean, just like in the context of improper integrals, is I want you to supply me with an argument which demonstrates whether or not this thing converges or diverges. Sure, the answer that you'd box, okay, I suppose, would be either the word converges or diverges. And so in some sense, you can flip a coin and be 50% of the time correct on whether this thing converges or diverges. You with me? However, I will severely ding you, even if you get it right, if you don't supply a correct argument for why you believe what you believe. Correct arguments rely upon the results that we've established and are taking as given results. So for example, things like the integral test, the p-series test, the divergence test, stuff about geometric series, all of that stuff is stuff that you can use without, sort of proving it or further justifying it. Here, we are going to use the integral test, okay, to investigate whether or not this thing converges or diverges. So if we use the integral test, then what we know is that integral test implies that this sum from n equals 2 to infinity of 1 over n log n and the improper integral from 2 to infinity of 1 over n log n, x log x dx converge or diverge together. And I claim that we can analyze this integral pretty easily. How? Well, take a moment. This is good review for you. I could very well find myself giving you this integral, like let's say on a midterm tomorrow. How would you kill this integral here if you were forced to? It might be a good moment to pause the video to think. Substitution all the way. This is substitution all the way. So what we're going to do is make a substitution of the following form. We're going to let u equal the natural log of x. Did you think substitution was going away? Let u equal natural log of x. Then du is equal to 1 over x dx, right? And look, inside that blue bean, that's du. So then we can rewrite this integral here as the integral of 1 over u du. This natural log of x becomes u. The 1 over x dx becomes du. Okay? And of course, when we do substitution on a definite integral, we have to adjust our bounds. So let's see. When x is equal to 2, all right, what do we get for our new lower bound? U is equal to the natural log of 2. All right? And if x is equal to infinity, look at the dumb thing I'm doing with my hands. Look at this. Look at that. That's so stupid. When x is equal to infinity, okay, what's the value of u? Well, really what we're asking is what is the value as x goes to infinity of the natural log of x, right? The limit as x goes to infinity of the natural log of x. And what you should know by now, because I've been hammering this point, is that it goes to infinity. Okay? So this integral is equal to that integral there. But what can we say about that integral? That integral is a p integral. This is a p integral. I mean, I know it's got u's instead of x's, and I know we've got this funny ass number down here, natural log of 2, but it's still a p integral. It's a p integral with p equal to 1. So this is a p integral, p equal to 1, which implies that this thing diverges. And therefore, the series diverges. This to me is a complete argument. Okay, this to me is the gold star argument. All right, for this particular series. This is the integral test in action. Okay, cool. Is n over n squared a p integral? Sure, but just cancel the n's, upstairs and downstairs. It's the same thing as 1 over n. It's not an integral either. And, I mean, fuck. No. Okay, the answer to your question, Big Yeef 88, is no. It's not an integral. Now, I know you can't write an integral very well in Twitch chat. But even if you were to put an integral symbol in front of there, you'd still have problems because you'd be integrating with respect to n, which I guess isn't so much of a crime, but you can. It's just a little bit weird. But if you were to write the integral from 1 to infinity, let's say, of x over x squared dx, that would be a p integral. Because you could cancel the x's from upstairs and downstairs. I sometimes wonder if any of the people that are watching are just like complete randos that are not part of the class, because this is, I guess, totally public. Anyway, I got 10 minutes. No, I got 5 minutes. 5 minutes. I want to do another example. Let's take a look at the sum from let's take a look at the sum. How about, let's see. I guess we already know some of that stuff. Yeah, let's just do this one. So sum from n equals 1 to infinity of, actually, you know what? Make you do this. I'm going to make you do this. This will be your post-lecture slip. And we'll call it a day. Because I actually only have 2.5 minutes, I'm noticing. Let's think about the sum from n equals 1 to infinity of n over e to the n power. Okay. So this is a infinite series. I want to know whether this thing converges or diverges. And I'm just going to tell you what you should do is use the thing called the integral test. Use the integral test to try to figure out whether this thing. So your post-lecture slip that I want to see in my email by the end of today. Oh, and by the way, so I tallied, the post-lecture slip thing. I'm getting pretty consistent responses from about 30 of you, but there are 17 of you out there that are just sort of ignoring it. I really advise that you not do that. These lectures slips along with the homework are going to end up being 18% of your final grade, so don't ignore it. I want you to test for convergence. Test what for convergence? Test this for convergence. Okay? And I'm going to give you a big hint because I love you. You ready? Use the integral test. Hints. This one's probably you probably knew this because we've been talking about the integral test a lot, and you're not stupid. So there's your first hint, and your second hint. This is the one where the love is. Okay, this is me saying I love you and I want you to succeed. Here is a hint to help you in your journey. Oh, what was the hint? Yes, this is the hint. Our good friend, integration by parts. I'm pretty sure. I don't know for sure. I mean, I'm pretty sure though that will be a helpful hint for you. So this right here, this is your post-lecture slip. I want you to test this in a series here for convergence, okay? And then I want to see that in your email. That's all for today. I just, it's 8:50 right now. Is something like the sum from 1 to infinity of 1 over n plus 2 squared also p-series? That's an interesting one. So let me just answer that question, but could think of this as being the end of the lecture, and I'll just answer this question here on stream. So by the way, I'm going to open up Zoom office hours in 10 minutes, okay? And the URL for the Zoom meeting is in the email that I sent you this morning. Holy shit, okay. So we have the sum from, the question is this sum, is this series, is this also a p-series? Well, here's my question. Where do you want me to start n from? Let's say that, I'm not going to wait for your answer. Let's say we start n at 1, okay? And we will go off to infinity, okay? I claim this is a p-series. Or it should be thought of as a p-series, okay? Because, all right, so what are the terms of this sequence? The first term of this sequence would be 1 over 1 plus 2 squared, or 3 squared, right? The next one would be 1 plus, so when n is equal to 2, 4 squared. 1 plus 5 squared is the next term, etc. Right? But we could just as easily write this infinite series here, then, as the sum from n equal to 3 to infinity of 1 over n squared, right? These are exactly the same infinite series because they both have as their sequence of terms starting at 3, 1 over n squared. This process of going from this series to this series, it has a name. It's sometimes called re-indexing. Maybe that's evocative for you and makes sense. This is a re-indexing process where we go from this presentation for the series to a different presentation of the same series, right? This series here, I think we can agree, is very close to a p-series. It is a little bit different in the sense that n starts at 3 here, whereas in the general expression that I've got here, we've got n starting at 1. But that's superficial, and nobody gives a shit. Okay? Yes, this is a p-series. Totally. Therefore, this is a p-series. Okay? Hopefully that answers your question. All right. So that's all for today. Hey, did you know there's a midterm tomorrow? I hope that you're on top of that and that you will show up tomorrow, because I don't want to have to give you a 0 out of 10% on your final grade there and drop you from a D to an F, because I'd rather just give you the full 10%. You know, that's what I want to be able to do. But you gotta show up. You gotta put in the work. Yeah. Okay. Okay, I'm a little giddy. Okay, bye. I love you all very much. I'll open up office hours in 7 minutes. Bye.